Hi guys, welcome to my physics lab, and in this fourth experiment we're going to be covering oscillations. So first of all, the introduction. The purpose of this lab is to track and model the motion of a spring using the tracker software, and then we're going to compare this observed motion with the predicted motion that we are going to build with a computational model. And finally, we're going to analyze if the movement of the spring follows the energy principle. As a preview of the results, we can say that the energy is conserved and then the motion of the object can be predicted. Here are some fundamental principles that we need to know before getting into the experiment. First of all, Newton's second law, and we need to keep in mind that the summation of the forces for this experiment is going to be the spring force plus the gravitational force, and we have the respective formulas for each one of these. Also, we have the energy principle that states that the variation of the energy of the system is equal to the sum of the work of the surroundings plus the exchange of heat. We know that the system is going to be this mass, the spring, and the earth, and we're going to assume that the surroundings are going to be nothing. So because of this, because we don't have any surroundings exerting forces on the system, we can say that the delta E is going to be 0. So delta E is also the sum of the energies of the system, which would be the kinetic energy, the spring potential energy, and the gravitational potential energy, and we have the respective formulas for each one of these. And additionally, we need to remember the position update formula as well as the velocity update formula. And finally, we have the period equation that we're going to use to find the spring force constant. Here is the tracker analysis. This allows us to see the initial conditions, like the initial position and initial velocity, and we can see from the graphs that our body follows an oscillatory behavior in both the x and the y axis. Also, from seeing the x graph, we can calculate the period, the estimated period, by dividing the time it takes from this high point here to this high point here by 5, because we have 1, 2, 3, 4, 5 periods in that time, and we get our period is going to be 1.519 seconds. So in order to find k, which is going to be the spring constant, we're going to input all of like the mass and the period into our period equation formula. In following this procedure, we get that k is going to be equal to 6.83 newtons per meter. Now this is a video that shows my computational model. I've written in code the formulas for the spring force, the gravitational force, and the energies. And here I am inputting the CSV file in order to get the graphs. Here we can see the change in energy versus time graph, as well as a little graph of how our spring is moving. And GlowScript also allows us to see the position versus time graphs in both with the model and the experiment. As a comparison of the results, we can see that both graphs are pretty close to each other. However, we can see in the x position graph that as time goes on, the difference between the data, between the model and the experimental data, seem to increase, while the y position one remains, we can say that it remains kind of close to each other. So some possible errors that could have led to this happening is that in reality, some forces in the surrounding could be affecting the body's motion, like the air, that could be offering some resistance. And also the period was only an approximation and wasn't as precise because we depended on the time steps from tracker. And also the precision of where the center of mass, if they were not accurately placed, then this would affect our data. Now for the further questions and what does it mean for your model, is the energy principle satisfied? We can say that yes, by looking at our graph. Throughout time, the summation between delta k, delta u graph, and delta potential spring energy sums to 0, and this is shown by this orange line that remains at 0 throughout the motion. And for the second equation, where it asks us to estimate the period of oscillation for x and y, we can see that they both differ, and this is the answer I get for both. And we can see that they both differ, and this is because the motion is not perfectly circular. If we recall to the motion, it's kind of elliptical, and this means that the velocities differ from the x and the y axis. Thank you.